This part of the lab is mostly about instrumentation systems. In these types of systems, we usually want a voltage that's proportional to the parameter we're measuring. An instrumentation system generally consists of a sensor, which converts what's being measured to some kind of electrical parameter, and an electrical circuit that converts that parameter to voltage. We'll design that circuit in this lab. This is a thermistor. If the temperature here changes, the resistance of the gauge changes. This sensor is what's called a negative temperature coefficient, or NTC thermistor. That just means that the thermistor resistance goes down as temperature increases. The first thing I need to do is characterize a thermistor. I want a range of resistances from about room temperature to the temperature of my fingers. I'll use a DMM to measure the resistance. When the thermistor is at room temperature, the resistance is about 11 kiloohms. If I warm my fingers a little bit and then pinch the thermistor to warm it, I get a resistance of a little over 8 kiloohms. Notice that the temperature measurements tend to be relatively slow. It takes a while to warm something up or cool it down, so you may have to be a little patient with this lab and allow the system some time to respond. In order to convert this resistance change to a voltage change, we'll use what's called a Wheatstone bridge. I'll talk about those next. This is a basic Wheatstone bridge circuit. The circuit has a fixed voltage, V sub S, applied to it across these terminals. These three resistors are all fixed and they have the same resistance R. This resistance varies. It's R plus some resistance change, delta R. We want to find the relation between this voltage difference, V sub BA, and the resistance change, delta R. This circuit consists of two voltage dividers that are in parallel with each other. The voltage V sub A can then be calculated from a voltage divider formula. V sub A is the total voltage, V sub S, times this resistance over the sum of these two resistances. Since those resistors are the same, this is just V sub S over 2, and it never changes. This side of the circuit is also a voltage divider. So V sub B is equal to V sub S times this resistance, R plus delta R, over the sum of these two resistances, which is this. So V sub B increases as delta R increases. From these relations, we can see that if delta R is 0, V sub A and V sub B are both V sub S over 2, and the voltage difference, V sub BA, is 0. Also, since V sub B increases as delta R increases, the voltage difference, V sub BA, increases as delta R increases. So if we put our sensor here as the variable resistance, we can get an output voltage that changes with the sensor's resistance. This circuit is useful from a conceptual standpoint, but it's difficult to implement without using really expensive precision resistors. In our parts kit, for example, the resistor tolerances are on the order of plus or minus 5%. That means that even if we have resistors with the same nominal resistance, it's very unlikely that they will have the same actual resistance. Another practical problem is that we would need to match the resistance of these three resistors with the nominal resistance of our sensor. Luckily, there's a pretty easy way to create a circuit that allows a lot of flexibility in what resistors we use for our Wheatstone bridge. I'll talk about that circuit next. This circuit doesn't require any of these four resistors to be identical, and it uses a potentiometer to do what's called balancing the bridge circuit. When the circuit's balanced, V sub BA is equal to 0. What we'll do is change the resistance of this pot to force V sub BA to be 0 when the sensor is at its nominal operating point. I'll use the sensor as this resistance down here. We don't have a wide range of choices of potentiometers in our parts kit, so I'll choose that next. What I do want to avoid with the pot is working at the extreme ends of the range of possible potentiometer resistances. The resistors R1 and R2 can be chosen somewhat arbitrarily in this circuit, but there are restrictions. this circuit still consists of two voltage dividers in parallel. I'll leave the math for you to do, but the general result is that if V sub BA is 0, the ratio of R2 to R1 plus R2 has to be the same as the ratio of the sensor resistance to the sum of the two resistances in the right leg of this bridge circuit. To balance the bridge circuit, I can set the value of the pot resistance by monitoring the voltage V sub BA with a voltmeter while I adjust the potentiometer's resistance. If I use this approach, I don't really care what value the pot resistance actually is. I just change the potentiometer position until the measured voltage is 0 when the sensor is at its nominal operating point. I just need to make a reasonable first guess for the resistances, and then the potentiometer can do the fine-tuning for me. Here's my bridge circuit. I'm using a 50 kilo ohm potentiometer here, so I have an available range of resistances of 0 to 50 kilo ohms. The nominal thermistor resistance was about 11 kilo ohms, so the expected potentiometer resistance should be well within the allowable 0 to 50 kilo ohm range of the pot resistances. The thermistor is connected across these two terminals, and the voltmeter is measuring this voltage V sub BA. I'm using the Analog Discovery Supplies instrument to provide 5 volts across these two terminals. My thermistor is at room temperature, so I want the measured voltage to be 0 under this condition. Currently, I'm reading about negative 0.3 volts. If I change the set screw position, the voltage changes because I'm changing the resistance in this leg of the bridge. Okay, now I'm getting about 0 volts at room temperature. Now if I warm the thermistor with my fingers, the voltage changes. If I want to change the signs relative to increasing or decreasing temperature, I can just switch the leads on the DMM. In this lab, we created a simple instrumentation system. I want to emphasize that this lab is intended to give you a feeling for instrumentation systems, rather than create a well-designed measurement. We're ignoring a lot of important details. The goal is mostly to give you an idea of how electrical circuits are used in instrumentation systems.